In the last video, we dealt with the situation where we were finding the maximum value and the minimum value of a function that was continuous on a closed and bounded interval. Now what we want to do is move to a situation where basically the function should still be continuous, but the interval may not be closed and it may not be bounded. And so what we have is we have another theorem that says this. Suppose f is a continuous function that has exactly one relative extremum on an interval, say at x0. If f has a relative minimum at x0, then f of x0 is the absolute minimum of f on the interval. If f has a relative maximum at x0, then f of x0 is the absolute maximum on that interval. So again, if we have a function that has precisely one relative extremum on an interval, its continuous function, then if that relative extremum is a relative minimum, it's the minimum on that interval. If it's a relative maximum, it's the maximum on this interval. Now this one is going to take a little more work because we have to not only find a critical point, but we have to show that it's a relative extremum. So let's consider this function. F of x is equal to e raised to the quantity x cubed minus 3x squared. So let's see, so the thing is, and we're on the interval from 0 to positive infinity. Notice this interval is not closed and it's not bounded. So the previous theorem said that if there's one relative extremum on that interval, then if it's a relative max, it's a maximum. If it's a relative min, it's a minimum. So we need to go looking for relative extremum on this interval, and we'd have to start, of course, by looking for critical points. To find a critical point, we look for where the derivative is either 0 or undefined. So let's take the derivative. All right, the derivative of e raised to the x cubed minus 3x squared is e raised to the x cubed minus 3x squared times the derivative of the exponent, which is 3x squared minus 6x. Okay, and now let's factor this. Well, there's not too much we can do with the e, the exponential here. But this 3x squared minus 6x, we could take out a factor of 3x. And we'd be left with x minus 2. And now we can find out where this is 0 or undefined. Well, the exponential functions are never 0. They're never undefined, assuming the exponent is, and it's not in this case. This is always positive. So when we set this equal to 0, this expression, I should say, will never be undefined, but let's see, where will it be 0? Well, this is never 0. This factor is 0 when x is equal to 0, and this factor is 0 when x is equal to 2. Okay, now let's see. X is equal to 0 is not in this interval. Be careful, because remember, this interval does not include the endpoint 0. It's an open interval, and so we don't really have to worry about x is equal to about 0, because it's outside of the interval. We do have to worry about 2. Now let's see. Now we know 2 is a critical point, but we need to know it's a relative extremum. It's a relative maximum or a relative minimum. So let's see. I think the easiest way to do that would be look at this derivative. Look at this derivative and decide whether, what's the signs of it on each side of it. Notice that this derivative is 0 when x is equal to 0. It's 0 when x is equal to 2. I don't really need to worry about what's going on at 0, but I do need to worry about what's going on at 2. So let's take a look at just to the left of 2, say at x equals 1. Well, e to this power, well, e to the any power is positive, so this is going to be positive, times when x is equal to 1, 3x is 3, so that's positive. And when x is equal to 1, x minus 2 is negative. So a positive times a positive times a negative gives us a negative result. So the derivative is negative here. It's decreased. The function is decreasing. At x is equal to 3, well, the exponential, again, is always positive. 3x is 3 times 3, that's 9. That's positive 2. Make this a little clearer. Okay, and x minus 2 is 3 minus 2, that's 1. So that's positive. So everything's positive here. So the derivative is positive. That means the function is increasing. So we must have a relative min at x equals 2. But that's the only relative extremum that we have on this interval because we don't have any more critical values on that interval. So it's absolute min. I think I have this worked out so that we can see what this is, so that I can express, when we look at this, I can see this. So notice at 2, there's a relative minimum. The first derivative is 0, but what is that relative minimum? Well, I have to evaluate this at 2. Well, when x is 2, I'll get 2 cubed is 8, minus 3 times 4 is 12. 8 minus 12 is negative 4. E to the negative fourth is roughly 0.018, and so the minimum here is 0.018 at x equals 2. So the minimum is e to the negative fourth, which is approximately 0.018 occurs at x equals 2. Okay, let's take a look at one more example. Let's take a look at this function. Find the maximum or minimum values of f of x equals x to the fourth plus 4x on the entire real line. Okay, well, again, this is not a closed or bounded interval, so we'll have to appeal to the second theorem. All right, so we'll have to first of all look for critical points. Remember, critical points are where the first derivative is 0 or undefined. So take the first derivative. So that's going to be 4x to the third plus 4. I can factor out a 4. All right, and I'll be left with x to the third plus 1. And if I look at this is 4. This is the sum of cubes, and if I can factor the sum of cubes as x plus 1 times x squared minus x plus 1. If you check that, when you multiply this out, let's just do this quickly. That's x times x squared is x to the third. X times negative x is negative x squared. 1 times x squared is positive x squared. X times 1 is x. 1 times negative x is negative x. And then 1 times 1 is 1. And notice these cancel. So this is the way that it factors. Notice then the critical values are going to be where this expression is 0. So we'll have 4 times x plus 1 times x squared minus x plus 1 is equal to 0. Well, that 4 is never 0. X plus 1 is 0 when x is equal to negative 1. How about x squared minus x plus 1? Well, to find out where that's 0, I'm going to use the quadratic formula. And let's see where this is going to be 0. X would be equal to the opposite of b, that'll be 1, plus or minus the square root of b squared, which is negative 1 squared, that's 1, minus 4 times 1 is minus 4, all over 2 times a, which is 2, and we can see right away that we have a negative number under the radical. The discriminant is negative, so there's no real solutions. All right, so the only critical value we have is at x is equal to, only critical value we have is at x is equal to -1. This one is easy enough that we could apply the second derivative to find out whether this is a maximum or a minimum. So let's take a look at x at f double prime. Notice we can only use the second derivative if this is a number that makes the first derivative 0, and of course it does. So the second derivative is going to be 12x squared. All right, and if we apply this if we evaluate the second derivative at -1, we'll get 12 times -1 squared, which is equal to 12. That's greater than 0. So we have a place where the tangent line is horizontal and we're opening upward. So we have a relative min at x is equal to -1. Since this is the only relative extreme, so this is the minimum. And I guess we could evaluate that pretty easily. Well, if x is equal to -1, all right, remember f of x is x to the 4th plus 4x, so that would be -1 to the 4th, which is 1, plus 4 times -1, so 1 minus 4 would be -3 is the minimum value and it occurs at x is equal to -1. Okay, and I think I have the picture of this here, and I notice I've shown you that second derivative test. Here's the graph of the function. Notice at -1 we're at -3, right, is the minimum value. Okay, so this is how we find the maximum and minimum on an interval that's not closed or bounded. A lot of times we have to be careful because functions just won't have a maximum or minimum on such an interval.